Well, welcome again. Um, well, this is where the rubber meets the road. We're starting off the course, and as you'd expect, with every course, there's that first set of administrative issues that the lecturer or author or whatever goes through. So in this prelude of about 16 view graphs, I'm going to go over a number of issues which, before anyone goes through the technical lecture material, would need to do. First of all, I'm going to use the style of this course, the same style as is recommended by MIT's OpenCourseWare. In other words, if I were just giving the lecture at a blackboard or presenting these view graphs with a laser pointer, give it naturally. There'll be places where I'll maybe miss a word, stutter a little bit. I'm not going to worry about them. The only time I'm going to really worry about re-editing is when I make a clear technical mistake that I don't correct myself for, and the rest of it is the humanity of Bob O'Donnell that you see. It's a much more natural style, and you'll hear those ums from time to time. And the second thing is I want to let you know that this, for me, is an exercise of joy. And although it's going to be a lot of work, I know, but it's also my gift to the radar community. And it's something I've wanted to do for a long time. And this is a course which I wish that I had to take when I got my PhD and I started working in radar and knew nothing about radar before that. I wish I had known the material in this course, and that's why I'm putting it down, so that people, as they're starting off in a career of radar, whatever their background was, but an advanced background. You know, this is not a NOVA styled radar course. There's an excellent course like that I put together with colleagues from Lincoln Laboratory. I was the lecturer. And that course is on MIT's open website, and its title is Introduction to Radar. And if you Google radar, video, and course, it comes up first. And we know it worked out very well for people who wanted a NOVA-style version, because in the first year, about 3,500 people watched the entire 12 hours, about 325 view graphs. This is a significantly more technically in-depth course. It requires much more knowledge of the preliminaries before you get into radar, a solid math background and an understanding of electromagnetism that's well above that of someone who's taken a general education course at a university their freshman year and had a smattering of electromagnetism. You really need a good background, and I'll go over that background with you. Okay, now let's move on to the points. This course was initially developed by me in 2000 as an introductory course in radar systems engineering for our new assistant staff, who typically, at Lincoln Laboratory, I'm retired from Lincoln Laboratory right now, our typical assistant staff is someone with a bachelor's degree in science or engineering, the physical sciences, and there's a smattering of backgrounds. An excellent computer science, computer engineering, physics, mathematics, mechanical engineering. We have one area people are working in biology, and if you can believe it, biodefense systems, they are working at Lincoln Laboratory, and you can need to do some measurements with radars, and people would like to know how they work. The typical profile of a student is a recent engineering or physical science graduate from a university. You should have, ideally, a bachelor's degree in electrical engineering and physics, is what I say, and mathematics. But having it in one or the other, you really, that gives you a good start. You're going to have holes, but a good start. Computer science or computer engineering or mechanical engineering, you're going to be more challenged. But many mechanical engineering tasks are needed to build a radar. If you're building a radar dish that's at the millimeter wave region, and you need to make that antenna, if it's a parabolic dish, exact to a parabola to a small fraction, say an eighth of a wavelength, tenth of a wavelength, and that, if the antenna is 100 feet in diameter, that is a very challenging mechanical engineering tasks. So there are a lot of tasks in radar that mechanical engineers, we radar designers couldn't do without. And now here's the thing that's going to be a challenge for many. You all should have a solid understanding of electromagnetism. Probability and random variables, and calculus through differential equations, and vector calculus. I had that background by the end of my junior year at MIT, almost 50 years ago, 48 years ago, something like that. And I've noticed, as I've looked at the curricula, for many electrical engineers, they don't have as solid a background in electromagnetism as you would need for this course, and they'd have to bone up some. And mathematics, particularly vector calculus, can be lacking. For the physicists, on the other hand, they won't have a good understanding at all of digital signal processing, which you should understand. And I'm going to give you ways of the physicists will understand probability from the wave equation, quantum mechanics, and which innately says that not like classical mechanics, which everything is clearly deterministic, that things are more broken down into probabilities. So they understand that formalism better. They understand vector calculus very well through working out the wave equation for Schrodinger wave equation. But there's a mix and match that different people will have. And so you should have, going into this, you'll see, and I think I'm going to put together at some time and post it. For the core lectures, I'm going to put on one side the techniques that you need, and on the other another axis, probably the columns, I'll put each lecture, because some people may just want to go in and understand radar antennas, and there'll be certain attributes from this list of general areas that you'll need. You'll be able to go in and see, okay, I'm good for these lectures. I have to bone up on these particular subtopics to get 100% out of it. Okay, now let's move on. The course evolved, about 4 times that I taught it. Each time I added a little more. This course is a significant evolution of the course that I taught at Lincoln Laboratory, in that it's more technical, a little more technical, and as you get to teach a course, as an old story from my history, you don't want to take a course from someone the first time they've taken it. The second time the professors taught the course, it's probably the best time. The third time they're getting a little bored with it. This set of lectures contains a very large amount of material. In the course section, which is 19 lectures, and you'll see what I mean by that course section in a minute, I have already put together and well vetted 17 of those lectures. And those 17 lectures constitute 1,152 PowerPoint view graphs, which is going to take a long time to go through. There are problems at the end of each lecture. And as you'll see, for me, a lecture is really a topic that will vary in length from, could be an hour, could be 2.5 hours, but those segments will be broke up. I'll get to that later. I'm jumping ahead of myself. At the end of every lecture, I'll have a clear set of references as to where you can get the material to bone up on if you want to look deeper into any of those subjects. And there'll be some cases where I'll give you an outline of how to solve a problem and the mathematics of the outline, but I won't fill in the details of it, but I'll tell you a book where you can see the details in much more depth, step by step. There's only so much we're going to be able to do, even in the amount of time that we have. And then I'm going to also have a section after the 19th lecture called Other Topics. And these are new topics that weren't in the original course that I taught at Lincoln Laboratory that I thought were worthwhile enough that they're specialized types of radars that not all people really need to know in what I call the core set of lectures. I've never seen a lecture or a chapter in a book on how you design a radar. Maybe there's one out now and I've missed it. I'm going to make an attempt to put that together. The use of radars in remote sensing. A lot of people in universities study radars because their real goal in life is to do remote sensing, and I want to have this available to them, and that's going to take some learning from my part. And over-the-horizon radar is a specialized topic because it works in a specialized regime of the electromagnetic spectrum at longer wavelengths than microwave radar, which will be the core of the course. And you'll see the outline for more of that sort of stuff. Who is this for? Well, this is for people with little or no previous knowledge of radar systems, but I've intimidated you with a lot of solid coursework in the basics of physics and mathematics that I'm going to expect you to know to get 100% out of this course. If you need if the words just don't make sense to you, go to that Introduction to Radar course at Lincoln Laboratory, and it will give you a NOVA-type view of radar, and you'll get the big picture, and then you can hone in on and take this course. And I mentioned the details of that earlier. You just go to Lincoln Lab's open website at www.ll.mit.edu, and on the upper right-hand side it says educational activities and workshops. You click on that, you'll find it. And also, you can just Google, as I said before, the Google address. The Google keywords to look for. We're number one there. What are we going to do? We're going to give the participants a start. I shouldn't have really said start. We're going to give you, it's going to be the beginnings of radar, but taught at an advanced level. But it's not at all a complete understanding of radar system issues and of radar's subsystems. The book, I'll get to the book and that issue. I mean, there are several 500-page textbooks just on the subject of antennas, radar signal processing, and other subsystems. There's a radar handbook that thick, and I'm not getting near those, although I do use them in many cases for references. And the reference material, as I said before, will be reinforced with illustrative problems from the textbook for the course, and they'll be presented at the end of each section. The next thing is, do the problems. I looked through all the problems, and I think that those problems which I suggest you do, if you really want to if you're serious about learning radar, you should do those problems. And that will make a really big difference in reinforcing these lectures. Okay, now the textbook. I'm recommending the third edition of, not recommending, it's the textbook. Third edition to Introduction to Radar Systems by Meryl Skolnick. And it's not the only book I'm going to use. I've read several score books, many of the chapters of those several score books on radar subsystems and systems, and I'm going to give you my 2 cents worth, you know, free advice is worth you pay for it, how I found them worthy and worthwhile. There's another new book out, which SciTech was kind enough to send to me, called Principles of Modern Radar, by a bunch of fellows from Georgia Tech. It covers, there's a significant overlap between that and Skolnick, and I think, as all teachers and authors do, that what they lecture, whereas I follow Skolnick and references problems, 85% of the stuff in Skolnick is also in the other book, presented in a different context. And the context that I presented in is different from Meryl Skolnick's, and it's different from Mark Richards. Mark looks, I think, at technology today and where it's going. Merrill's looks an awful lot. Remember, there's a third edition and one every 20 years back, where radar has come a lot and not enough where it's going. What I hope to do is to combine both of them, because when I learned these topics, when I learned radar systems, I was in the middle in age of the two of them. You know, Merrill's in his 80s. I'm really not sure what Mark's age is. He's certainly not 69, my age. But I have that middle perspective, which we'll go into further, and you'll see I will infuse in you that radar is not a dead art. It is evolving. And I'm going to point out a lot of the time the evolution of it by talking about things that were 10 years ago, 15 years ago, and so forth, to show you the slope and how particularly the development of microwave integrated circuits to use in that technology to use in transmit receive modules, and the development of high rate and high sampling rate A to D converters, and the giant revolution that Moore's law has brought us in the digital processing world has led to a huge number of these revolutions in radar that have happened over the course of my career in radar of 40 years. And these kinds of technology revolutions will continue. And so this is I want to show you this slope. This isn't the be-all and end-all, because the slope is way out there still going. And to give you an idea why I felt that this course was needed, I was doing some work at pro bono work at the University of New Hampshire and curricula, and I looked up on the websites of the top 50 university ECE departments. That was a U.S. News and World Report 207 rankings. I examined them. And of the top 50 schools in EE and ECE, only 10 offered a radar systems or a radar and remote sensing course. And half of them, the course was only half radar. And the textbooks used at the time, this was before the one by the fellows at Atlanta, at Georgia Tech, half of them used Merrill Skolnick's. One used a radar book by Lebanon, called Radar Principles, which is very mathematical in nature. And one used no text journal articles, and 3 of them I couldn't get information on. Okay. Now here's the core outline of the course. Next I'm going to give you the big picture of radar, an introduction. And then I'm going to give you reviews of electromagnetism and then of signals and systems and digital signal processing. Each one of these 3 topics should be a course, and you should have it under your belt. Now, what I'm going to do, in one case 40-odd view graphs, and in the other case 70 view graphs, is to go over in probably 40 or 50 minutes and then maybe an hour and a half those view graphs. And I will not teach you the subject, but I will show you the areas in those subjects that you need to be extremely facile in. Now, in electromagnetism, physicists spend an enormous time on electrostatics, and they solve Gauss's law for all kinds of systems like that. And it'll be weeks, a couple of weeks of the course going over Gauss's law. We don't need it. We need to understand Maxwell's equations, which cover all of electromagnetism, and a bunch of other things you'll get to see in the overview. And I'll do the same thing with digital signal processing and signals and systems. Then we're going to look at a lecture on the radar equation. It's the equation that links together the properties of the target, the properties of the radar, and the distance in between the two. And it says, will this radar work? And it's the sort of the brain of all the different subsystems in it. You'll see when we go over the block diagram of a radar. Then we're going to look at propagation, because the radars, unless they're in space, are going to have to propagate through the atmosphere, unless they're in space looking at space. If they're in space looking at the Earth, they have to go through the atmosphere. And then looking at the detection of reflections from signals, the target of interest, and noise. Both of these are random processes, and so we're going to look at the probability of detecting a target in the presence of noise that the system is generated at, its ambient background noise, and how we understand those probabilities. Then we're going to look at how big electromagnetically the target seems at microwave frequencies. Now, you're looking at me with your eyes, which are at the wavelengths of light, and that's the optical region. And their electromagnetic waves have the area of what you see. Okay? It's basically the area. Now, when your wavelengths get much bigger, resonance effects take place, and you go into the so-called Rayleigh region, and we're going to go over how you do accurate calculations of cross-section, the size of the target, and it's in units of area. Next, we're going to talk about antennas, which take the energy that a transmitter will generate in the microwave region, that electromagnetic energy, and focus it in one region so that you can focus that energy to see the target better rather than if the energy went all over space. And you'll obtain from the antennas usually a good understanding of the azimuth and the elevation of the target that you get the reflection from. That's a big part of the course. We're going to take 2 sections for that. Two what I call lectures. Then we're going to look at radar clutter. And that's the stuff that's out there in the actual world that you don't want to see. And then waveforms that you send out, and so-called pulse compression techniques, where we're able to get better resolution than the width of the pulse itself that we send out. And then techniques on how we reject moving, unwanted targets that are in the real world. How we separate a fast-moving aircraft from a slow-moving rainstorm that you reflect energy off of. We'll look at the difficulties, which I'll explain later, when you put radars on aircraft, so that with the Doppler effect, you measure the relative velocity. Well, if the ground's moving relative to you, that's a much harder clutter problem and clutter rejection problem. We'll look at that whole problem in one lecture. Then we'll look at observables and tracking in 2 parts. How we get the observables, the range, the azimuth, the elevation, the size, and the art of getting the best known set of observables, and then how we develop tracks of actual aircraft or missiles or whatever moving object in the sky you want to look at. Or if you're looking at hazardous weather, you know, how you get the best estimates of the weather amplitude, whatever. Then we'll look at transmitters and receivers, how they're made, and the block diagrams of those. And then we're going to take some time. I just want to point out here for a minute that it's up through transmitters and receivers that I have all the view graphs made for, ready to rock and roll, and I'm going to start videoing them now. Actually, the first 2 lectures, the Prelude, this one, which I'm redoing now, and the last part of the introduction, which I'll be doing in the next day or 2, have to be. I have the PowerPoints of the first 17, and most of those 17 I haven't videoed yet. But I'll be jumping right into those, and you'll see on the web page, or you saw in the web page if you got this far, my tentative schedule. Then I'll be developing, and it'll take a little more time, adaptive processing, and synthetic aperture radar, which is a mapping technique. That's all I want to talk about it now. Now, outside of the core materials, here are the different topics I'm going to talk about. You can just read them. I'm going to go over them in the introduction, a view graph for each topic, and all of the different lectures. And as I said before, the total of each topic may vary from about a half an hour for some of these additional material topics to 2 hours or so. Most will be the order of an hour. And I'm going to break up the video stream into what I call easily digestible pieces of about 20 minutes to a half an hour, so that you can look at part 1 and part 2 of a lecture and then go back to part 3. It's like a track on a CD. If a CD of a video, an audio book, is all one track and you only have listened to half of the opera, there's no way to get back into that half of the opera without running it forward on a CD. You'd like it to be broken down into tracks. And so these 20-minute or so pieces that I'll be breaking the videos down into will hopefully help you out with that. Okay, now to start the nuts and bolts of the academic credit issue. This is designed for very advanced seniors. It'll be a real challenge for seniors. Honor students, I'd say, who really have a good understanding of E&M and all those electrical engineering topics that I talked about, and have taken some vector calculus. Or first-year graduate student. It's a good first-year graduate course if you've built up the math and E&M background. If you're interested and your university doesn't teach or regularly teach a radar systems course, you could ask your faculty advisor for the name of the faculty who could oversee this course with you. Remember, you're going to have the problems, the book, and the lectures. And communications professors, communication systems professors, ought to be able to pick and choose from these lectures the right set for you as you develop on towards your doctorate or master's degree, and assign them. And the solutions books is available to a faculty member who's teaching the course from the publisher. They hold it very tightly at McGraw-Hill. And finally, they could develop a term paper, or in the back of Dr. Skolnick's solutions book, or a list of term papers that you could do for a final. And also, I'd like to develop in the future a methodology for students to take this course for transferable university credit via distance learning technology. And if you're interested in this, I've set up a special website for all queries relative to this course. And it's bobradarman@gmail.com. And so I'll be checking daily to see if anyone even looks at the course. Now, actually, we're going to have bleeds to see. But I'd like to let me know what you think of the course and how it's going. If you see any errors of any kind in this, let me know. It's very important that I upgrade the PDFs. If a part of a video is unintelligible, let me know if I didn't spot that intelligibility, that section, so that I can go back and think about it and record that chunk of the video. Because my goal is to teach you, okay? And so please communicate with me relative to that, and be patient with me as I put together these videos. I'd like to thank an awful lot of people and institutions who have been extremely helpful for me in this radar education product, and in radar education products while I was employed there at MIT, particularly MIT. I'd just like to mention, I'll mention some of them later, my associate division head at the time, Ken Roth, Eric Evans, who was my division head, and Dave Briggs, who was the director of the lab, who allowed me the time in the laboratory to develop that first course. The laboratory has been very kind to me in retirement. I'm not a laboratory employee. They've allowed me to use a significant number of Lincoln Lab copyrighted and previously released view graphs and photographic images from that previous course. At one time in 2002, Dr. Evans and I taught a radar tutorial at an IEE conference that was in the UK. And I've used a subset of those view graphs and some other view graphs also that have appeared. And the whole total of the Lincoln Lab view graphs is 125 out of the 1,100 and so forth. But one thing I have been scrupulously to is to get credit, get permission from any copyrighted piece of material. And to get that permission in writing, and also to give credit and let you know that where that view graph or where that open source material came from. Okay, a lot of the material in the course is mine, and I take credit for that. But and I apologize for that. But if I'm using an image, I have gotten permission to use it. Now, for Lincoln Laboratory, when I use their copyrighted material, I would say courtesy under the view graph if it's the whole view graph, or if it's an image from a view graph, I'll say courtesy of Lincoln Laboratory, used with permission, and I have all their permissions in writing, view graph by view graph, from the release source, and I've gone over with senior level staff officials in the lab, all those view graphs. Also, the same goes for my corporate friends who have friends and colleagues that I've gone to the institutions about copyrighted material, and I'll get to those some thanks later. Permission to use any copyrighted material, view graphs or images, or other copyrighted material must be obtained by you, but if you want to reuse any of it. The people have given me permission so that they can be put in PDFs and you can download them for your personal use. And you'll see the access for the how to get the PDFs. But there's no, this is the same boat as MIT's OpenCourseware. No provision is given by me for any of my material, which is delivered through this, for anyone to use this material for commercial purposes. And I'll go through the copyrights of this material and how it is some more. But more on to acknowledgements first. I'd like to thank the IEEE's Aerospace and Electronic Systems Society, the Board of Governors, for supporting me for the computer equipment, the PC, the webcam that this is on, and also the server that's located at the University of New Hampshire, and funds for the O&M to generate this course material. Without that pecuniary help, monetary help, I couldn't do this work. This is going to be hosted on two places: the IEEE's e-learning library, and Steve Welch and Jill Bagley of the IEEE staff have given me their verbal okay that it will be hosted on their site at no cost, and you'll see further information when you get to it. As of this day, I can't see the that I'm doing this Prelude in early February. Their site isn't up and running, but the New Hampshire site is. I'd like to thank the general sponsorship of the New Hampshire section of the IEEE. I've been elected by them as their chairman for educational committee for the section, and I'm doing this work under their auspices within the IEEE. And most importantly, I'd like to thank the Computer Sciences Department of the University of New Hampshire, who have allowed me to hook into their web connection and install this server that we're using, the IEEE-owned server, into their connection so that we could run this through their website. Scott Valcourt, who originally worked in the Computer Sciences Department, now works for their IT department, has given me the web support to hook up the Dreamweaver webware that I've developed, and he's helped me debug the links and things. I'd like to thank Scott very much. Without him, I just would have been lost in doing this. And next, I'd like to go back to the major radar contractors and also a lot of other individuals and contractors and associations who have allowed me to use their photographic images of their products. Among them, Raytheon, Northrop Grumman, Lockheed Martin, and Boeing. I've gone through their corporate offices, and I've gotten permission. I've got emails from all of them to use images. It's from their PR websites for the most part, or I've gone through, sent images to them, and they'd okayed them, and I've got all of them in paper. And whenever I use any of their material, It's cited, courtesy of XYZ Corporation, say Raytheon, used with permission. That means no one else has the ability, the right to use that permission without going back to them and getting it. If the words used with permission are not there, that means those are public domain or not copyrighted under U.S. law, but may be copyrighted under the copyright usage that I use, Creative Commons. We'll get to that in a minute. A diligent effort, I said, and I want to go over this, has been made not to use any copyrighted material without the owner's consent. There are a significant number of previously published line drawings, which I have myself, with Adobe Illustrator, re-rendered or redrawn, using so that I do not infringe upon their copyrights. I have been extremely diligent in learning copyright laws. So if you look and you say, hey, that line drawing is in another book, I've made my own line drawing from that using Adobe Illustrator, and that the experts at MIT's OpenCourseware and at the IEEE tell me makes it my copyright, which is the Creative Commons I'll get to in a moment. Except for the copyrighted material acknowledged in the lectures and reference material, all the material in this course, these view graphs and the video material, constitute a copyrighted by myself, Robert M. O'Donnell, under Creative Commons license. And it has the Creative Commons has a number of different licenses, meaning if it's you can be licensed for no attribution, you can use it for any purposes, anyone can use it. The one I'm saying that you have to do is you have to, if you use a photograph that I took the photograph of, you have to attribute it to me. And likewise, I attribute it to those people where I got from Flickr, where there's a huge number, or on Wiki Media, there are a large number of Creative Commons type licenses. And also I reinforced earlier and again, non-commercial. What that means, and share alike. So that they may not used for commercial purposes, they may be shared and freely modified subject to the above restrictions, and you can go to the website that's noted here for the details of that license. This does not mean that it's worthwhile noting that there is an addendum to the copyright laws called the fair use practice, that if material is used solely for education uses and with no profit involved, like by a university professor, that this material, particularly the PDFs, can be used for educational material that's no profit, not-for-profit corporation, understand, and you can just go ahead and use these PDFs on a screen for a course that's given where no profit is generated by the lecturer except their salary, by the university, which is a non-profit. And if you have any issues of copyright infringement, please contact me immediately through that email, and I will deal with them promptly. Thank you very much for that issue. And now my note. Okay. As of December 10th, it's now well into February. That's where I was. I've got I have a few minor illnesses. Let's see, that was 10th. Yeah, I can leave out that illness. In January, I fell down coming out of the local library and got a concussion, and that wiped me out for a while. So it's been a little time before I got to this. So 90% of the core material has been finished, and I've reviewed it. And as I said, I've got really good feedback from colleagues. A few things have slipped through, and please let me know. And as I said before I put them on the web, I'm going to edit the videos myself. And even in this process, stuff is going to leak through. And I'll be putting out an errata sheet and then crossing off as I fix the erratas easily on the PDFs for the courses. And then if there are enough errata that leak through a video, I'll redo the video, or I may just, you could keep a note while you're watching the video at slide such and such this time. The wrong thing was said, and it'll be refixed in the editor. I hope you'll really understand this. The goal is not to wait a year or two before I put the whole system on the web. This is a work in progress, and you're going to see the work in progress and see that I will be working steadily, barring some unforeseen event. And communicate to me, you know, any kind of error you see, and all of them hopefully constructive. And I heartily request them from you, and you can send them. And I'll usually send you a note back, thanks a lot, and that means it's being dealt with. Last view graph. I'd like to second to last. I'd first like to dedicate this to my dad, who is an educator, a lifelong educator. And I guess I've got something in my genes. My mother was a teacher, teachers are aunts and uncles all over the place. And also to my sons, Michael, my oldest, Megan, who's maybe she and Dave have made me a proud grandfather for the first time, and Megan is teaching assignments in graduate school, and to both Brian and Andrew, my younger children, not so young, they're both in graduate school. One at Ohio State studying electrical engineering, you know, and give the Buckeyes a yahoo. And my son, Brian, who is now contemplating where to do his PhD at one of 2 or 3 very, very good institutions, which he looks like has been accepted to. My wife, Janice, so much for her patience and love and understanding in dealing with me, if you knew me. We get together so long, almost 30 years that we've been married. I love her so dearly. And now I'd like to give a special note to those people way, 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 way back who early in my school years and early in my career didn't just write on a blackboard and give me homework, but they nurtured and challenged me and influenced me in the physical sciences and engineering. And they go over the raft from my late high school years. Sister Mary Seraphim of the Sisters of St. Joseph. Obviously, I went to a parochial high school, St. Mary's High in Lynn. And also in that note, that was the Sputnik time. And at MIT, they developed a new way of teaching high school physics, which I think has influenced high school physics a lot. Professor Zacharias, who's obviously probably by now passed away. If he hasn't, I apologize. But he and a team developed a physical science study committee physics course. And my high school was honored to be one of 21 in the country to test it out in a beta test. And that just grabbed me and just said, boy, this physics stuff, this physical science stuff is great. And it influenced me very, very strongly. And I went on to go to MIT. My freshman physics professor that I did recitation with was Hans Mark, who has a career that has moved. He's in his 80s at the speed of light. You know, I don't think he got tenure at MIT, but then he went to Berkeley and was heading the nuclear engineering department. He headed the Ames NASA Research Center. He went to the Pentagon as an assistant secretary of the Air Force, and he was head of the National Reconnaissance Office. This is all like a rocket stream growing up. You know, deputy director of NASA's Ames Research Center, and then the National Reconnaissance Office when it was black. Now you can talk about it. And then he moved to deputy director of NASA, and then he became the head of research and engineering for the whole Department of Defense, and then became, if that wasn't enough, he went on to become the chancellor for the entire University of Texas school system. And in that capacity, he was given an award as the best teaching professor at the place. And boy, he was mentoring, one of the best mentors I've ever run across. Dave Frisch, who really has passed away at my age, I think 68, 69. And he was just a fantastic mentor of a young undergraduate. And Herman Feschbach, a neighbor, who was just a very kind mentor, but I never took a course from Herman. My thesis advisor, Walter Solov, at the University of Pennsylvania. A couple of the professors, Henry Pimicroft and Herb Callan, that were just so motivating. And Dave Kramer at MITRE, who really, I say, Dave's retired from MITRE. Dave was an MIT control theorist who went to the MITRE Corporation well ahead of me. And I, so to speak, did a postdoc in radar, learning from Dave. And to Ed Mewey, my first group leader at Lincoln Laboratory, Ed was just such an incredibly creative, brilliant guy to work for. And lastly, two guys that are now, yeah, they're like me, retired, but they're working part-time. Bill Delaney, who and Dave Briggs, who was director of the lab, and now they're director's office fellows and director's office emeriti, whatever, for their decades of guidance and mentoring to me in my career. Lastly, a very, very special dedication. In memory of Roger Sudbury, who this past August succumbed to cancer after 3.5 years. He's just such a special fellow of mine, friend and mentor, and an IEEE fellow, and just an employee of MIT for decades and decades, from technical staff to the executive officer for the laboratory. And in the presidency, that would be chief of staff. And he's a former president of the IEEE's Microwave Theory and Technique Society, an officer and longtime member of many of that society's offices, and in the national IEEE level. I give special dedication to Roger. And while he was with us, he helped an awful lot in mentoring me through getting this material released from the laboratory, and so many other issues over where our careers overlapped so much. God bless him.